we have learnt about resampling techniques like jackknife and bootstrap. So, we have learnt in details about bootstrap and another associated technique, that is the jackknife, and we have learned how to implement bootstrap for different scenarios or different problems in R. In this session and in the next session, we would be learning about 2 more variants of resampling technique, but we will not be going into a lot of depth in those 2 techniques. So, we would learn what are these 2 techniques and we would see simple implementation of these techniques in R. In today's session, we would be specifying one technique which is called the permutation test. So, I would be speaking about the basic idea of permutation test and how we can implement a permutation test in R. In today's class, we would be learning about permutation tests and how to implement a simple permutation test in R. There are packages in R which implements permutation tests, but we will not be dealing with that. Rather, we would be writing a script in permutation test to see how actually a permutation test works. So, we would create a small data set and then see how to implement permutation test in context to that. Now, the idea behind permutation test is like this, that while testing for any null hypothesis, we need a test statistic, and the test statistic has different values under different alternatives. Now, what we need to do is we need to compute the sampling distribution of the test statistic, assuming that the null hypothesis is true. Obviously, in classical testing, there are some test statistics, and for some null hypothesis this can be done analytically, and then from that we can calculate the p value, assuming that the null hypothesis is true, and we can base our decision whether to about the hypothesis that we are considering. Now, there can be situations where it is not so easy to compute the sampling distribution. A permutation test gives a simple way to compute the sampling distribution for any test statistic. Note that for any sampling distribution that we need to estimate, we need to have many values of the test statistic. So, we need to generate many samples under the null hypothesis, and for each of the samples we need to calculate the test statistic, and from there we can have a sampling distribution of the test statistic. Now, assuming that the null hypothesis is true, now consider the case where we want to see the effect of an exposure on the outcome. If the null hypothesis is like there is no exposure, no effect of the exposure on the outcome, then changing the exposure would have no effect on the outcome if I assume that the null hypothesis is true. That means, if we randomly shuffle the exposure, we can make up as many data sets as we like. Assuming that the null hypothesis is true, or under the null hypothesis, all of these shuffled data sets should look more or less like the real data. If they look different, then we have reasons to believe that the null hypothesis is not true. Now, this is the basic idea about permutation tests. So, the ranking of the real test statistics among all of these shuffled test statistics, that is test statistics obtained from the shuffled data, should give a p value. Now, we can implement this using in R. Just to understand how a permutation test works, we can implement this in R by creating a small data set and see how we can implement permutation test on it. Now, to do that, we first set seed equal to 1 for reproducibility, then we generate a variable called trait. So, we want to see whether a particular trait is present or absent. So, let 0 indicates present and 1 indicates absent, and let us say it is present in 100 cases and absent in the next it's absent in the first 100 cases and present in the next 200 cases. Now, suppose y is our response and we generate y from our normal 0, 1. So, we take 300 random normal variables for 0, 1 and null dot y is r norm 300. Under the alternative hypothesis, we also generate a response which is all dot y, and that's generated from r norm, but this time the mean is taken to be trait by 2. So, for the first 100 cases the mean is 0.5, first 100 cases the mean is 0, while for the next 200 cases the mean is half or 0.5. So, for null y trait has no effect and for alternate y trait has an effect, and we know we can test this using the conventional t test. So, if we use t dot test null dot y explained by trait, VAR variance of equal variance, because we know that the variances are equal, we see that the p value comes out to be 0.3394, which means that trait has no effect on null dot y, while if we run the same test for alternate dot y, we get a p value of 0.00164, which means trait has an effect on y. Now, let us see what is the difference in the means for under the null hypothesis and for trait equal to 1 and trait equal to 0 under the null hypothesis. So, we call it as null diff, which is mean null dot y trait double equal to 1 and mean null dot y trait double equal to 0, and the null difference comes out to be minus 0.1129546. While for the same, if we perform the same thing, then the alternate difference comes out to be 0.4065713. So, we see that the null difference is closer to 0 than the alternate difference. Okay. So, now we would be creating a small function, and what does it do? This function is called one dot test. So, it samples from x, and then where it samples from x and we assume that x takes the value 0 and 1, and then we find the difference between the one group with the difference between the difference between the two groups, the difference for x star equal to 1 and the difference for x star equal to 0. So, this would give many true nulls. So, what we can do is we can use the replicate function now, replicate 1000. So, replicate 1000 times one dot test, and instead of x now I am providing trait. So, what it would do is it would sample randomly from trait, and instead of y it would use null dot y. That means it would reshuffle the data, and for each of the reshuffled data it would compute the null dot difference, or the difference between the two trait groups, mean difference between the two trait groups when the null is true. Similarly, we can use many dot false null, which is the same, but this time null dot y is replaced by alt dot y. So, that is the difference of the two traits, that is trait equal to 0 and trait equal to 1 under the alternative hypothesis. Now, if we run this, now we see the histogram of many dot true null, and the histogram, on the histogram we can add where exactly is our null dot difference value for the original data set, and then we can calculate using how many absolute values for many dot true null is greater than our computed null difference from the data set, and it comes out to be that 350 of them are greater than, or the computed the permuted many dot true null. So, the absolute value of those 350 of those, or 35% of those are greater than absolute value of the null difference that we have got from our data. Now, if we take the proportion, we get the value to be 0.35. Why we are taking mean? Because it is by 1000. So, when we are dividing by 1000, so 650 into 0 plus 350 into 1, divided by false is coded as 0 because it is a binary variable, and true is coded as 1. So, 650 into 0 plus 350 into 1 divided by 1000, and that comes out to be 0.35. So, the proportion of, so on 35% of the observations for the permuted data sets are greater than whatever we have observed. So, the p value here comes out to be 0.35. Now, if we do the same procedure for false null, what do we get? First, the false null value, if we see this red line is outside or at the right side end of the histogram, and if we do a table of that, we see that only 2 values are in the permuted data sets. Out of 1000 permuted data sets, only 2 values are such that the null difference for those are greater than the observed null difference for the alternative hypothesis. And if we, so here the mean that we compute here, if we compute the mean, so that means the proportion that we are computing, it comes out to be 0.002. So that means using permutation test, we are getting the same result as that of the t-test. Now, a point in permutation test is that it is useful when we do not know how to compute the distribution of test statistics. So, what we do is we take random reordering of the data and then perform the statistic, and for each of those reorderings we get a statistic value. From that we can calculate the sampling distribution of the statistic, and hence we can base our inference on the sampling distribution of that. We have learned about the technique of permutation tests. So, we had just an idea about what permutation tests is. When the sampling distribution of the statistic is a bit difficult to compute, or it is not straightforward, what we can do is we can take random permutation of the data sets and compute the statistic. And from the observed statistic or sampling distribution of the statistic, we can base our inference. In the next session, we would be learning about another new technique in resampling, that is called the cross validation. So, again in that session we would be talking about this cross validation technique. At the same time, we would see how to implement cross validation technique or the different forms of cross validation technique in R.